Example 6, we're going to look for the sum of a finite geometric sequence. So the sum of the finite geometric sequence, this sequence here, with common ratio R1, is given by S sub n equals the sum of the first term to the nth term, a1 r to the I minus 1, so it's finite. And then, so we have a sub 1 times 1 minus r to the n all over 1 minus r. So we're going to use that formula in order to find each of these sums here. So for this first example, we know that a sub 1 is 4, and then the r is 0.3. So all we're going to do is we're going to plug it into the formula. So the sum of the first 12 numbers is going to be 4 times 1 minus 0.3, and that should be in parentheses, raised to the 12th power over 1 minus 0.3. And so then it's just calculator work at this point, making sure you were plugging enough parentheses and so forth, and you would find that the sum is 5.714. So go ahead and try this example on the right. So if you tried it out, you should have gotten 2.667 here. Now it's important to note when using the formula for the sum of a finite geometric sequence, make sure that the sum is in this form. So notice number 1 that I has to be 1, the ending term is n here, and then it's I minus 1. And so for a sum that is not of this form, you have to rewrite it before applying the formula. For example, if you have I, and then it goes I equals 1 to the 12th term, then it's 4 times 0.3 to the I, then you have to change it a little bit because we need it to be I minus 1. So in order to do that is you have to do 0.3 times 0.3 raised to the I minus 1. And then, so notice we can just drop the parentheses here. And then what happens is this is in the front, and then you are finding the sum of the series using these values right here. Or some of the sequence, I apologize. And then so you really have that 0.3 outside because we had to take 1 out in order to do the I minus 1. And then it is different. So if you tried to find the sum without the 0.3, you would find that the answer is different. And so just know that it has to be in this form. Another note is that there is one of the assignments, one of the homework problems, it says it's 0 to 21 or something like that, or 0 to 20. And so again, that I has to be 1. So if I moved it to 1, what does the top number need to be? So it's going to be 21. And so it does change what value you plug in for that exponent there. So something to kind of keep in mind with this formula is that it does have to be of this form that is right here. So now let's look at the sum of the terms of an infinite geometric sequence, and it's called an infinite geometric series. Here. And so notice that if r has to be less than 1, the absolute value of r has to be less than 1, then the geometric series has the sum using this formula here. Note that when r is greater than or equal to 1, the series does not have a sum. So we're going to find each sum. We have, so n is 0 to infinity. So notice in the formula here that I is 0 and the infinity is right here. So that kind of helps us out a little bit. And then we notice that a sub 1 is at the top, our first term divided by 1 minus that ratio. So what I'm going to do in this case is I'm going to go ahead and use fractions. I think that's nicer, and then actually in the homework it does use that because it does work out very nicely. So what I'm going to do is change the 6, so 6 over 10. And then that reduces to 3 over 5. So this is 4 3/5 to the nth power. So let's apply that formula. S equals the first term, 4 over 1 minus 3/5. So this is going to be 4 over 2/5. And then 4 divided by 2/5. So just to kind of write it out, that is really 4 times 5 over 2. So 2 goes into 4 2 times. And so we find the sum of this series is 10. So it's really, really nice. Okay, here we're just given a sequence here. So a sub 1 is 3. Let's find our common ratio. Our common ratio is 0.3 over 3. And then so that is 0.1, or that is really 1 over 10. So let's do the sum of the series formula. That is 3, the first term, over 1 minus 1/10. So we find that's 3 over 9/10. So that's 3 times 10 over 9. So 3 goes in 3 goes into 9 3 times. So therefore the sum of this series is 10 over 3. So instead of using your calculator, putting everything in decimals, go ahead and use fractions. It works out very, very nicely. So try out these examples down here. So if you tried it out, you should have gotten 10 for the first one and then 25 over 4 for the next one. It works very, very nicely there. Let's do example 8, increase annuity. So an investor deposits $50 on the first day of each month in an account that pays 3% interest compounded monthly. What is the balance at the end of 2 years? And so looking at compounded monthly and everything else, we need to remember our formula. A equals P times 1 plus R over N raised to the N times T. So N tells us how many times it's compounded per year, R is the rate, and then P is the beginning amount, the principal. And so let's plug in what we know. So we know P is 50, R is 3%, so that's 0.03. And then it says it's compounded monthly for the first year, so N is 12. And the time we want is 2. So first let's plug it into this formula. So A equals 50 times 1 plus 0.03 over 12 raised to the 12 times 2. And so what we find is that this is 50 times, and you plug this in the calculator, you get approximately 1.0025 raised to the 24th power. And then, so this would be A sub 24. And then if we did A sub 23, it's going to be 50 times the same thing, 1 plus 0.03 over 12 raised to the 23rd power. And then if we go all the way down to that first one, that's going to be 50 times 1 plus 0.03 over 12 raised to the first power, which is just our 50 times 1.0025. And so we need that because we're going to write the sum of this series, A sub 1, 1 minus R n over 1 minus R. Then we plug in that A sub 1, which is this one. So that's 50 times 1.0025. And then the 1 minus R over N, right? We're plugging 1 minus R over N over 1 minus R. So this is 1 minus the 1.0025 raised to the 24th power over 1 minus 1.0025. Okay, so we're just plugging in those values, the R value here, this is our R, this is R. And then when you plug it all in your calculator, making sure you're plugging in enough parentheses, you get approximately 1,238.23. So the next question, you do the same exact thing. So an investor deposits $70 on the first day of each month in an account that pays 2% interest compounded monthly. Find the balance at the end of 4 years. Now it depends on whether you round or not, and that may change a little bit of what the total value is. But just try it out, see what answer you get here. Now, if you tried it out and you rounded, you should have gotten probably about $3,503.75. If you could plug it in without rounding, the book says that you should get $3,585.